Many thanks for the kind introduction, and I would like to thank the organizing committee of WCC 2020 for inviting me for this talk. So, this is basically an introductory tutorial on machine learning for healthcare audience. And without any further delay, let me begin by introducing you uh, to defining what machine learning is all about. So, machine learning is a subject in computer science whose goal is to develop computer programs that mimic or imitate the cognitive learning that happens in human beings. Here, I would like to emphasize the word imitate and mimic because these are programs whose intent is merely to imitate the process of learning and not to reproduce or copy the exact process of cognitive learning that happens in human beings. This is, of course, because humans themselves don't understand how cognitive learning happens inside their brains. So, if one has to exactly replicate the process, it would be an impossible task, right? So, the goal in machine learning is not to reproduce or copy the exact process of cognitive learning, but is to merely imitate or mimic the kind of cognitive learning that happens in human beings. And because it's basically a process of imitation, the computer programs are essentially statistical models and not models of human brain or something like that. Okay. And Of course, this gives the machines uh, an apparent picture that they are actually their cognitive abilities are improving, right? Because they imitate the process of learning, thereby it appears that the cognitive abilities of a computer which is running such programs actually improves, and the hope is with these apparent improved cognitive abilities, the computers can now solve problems which are complex and far beyond the reach of human abilities, right? Um, and since the end goal is to solve complex real world problems using human like cognitive abilities, this is what makes machine learning very attractive or at the same time challenging, right? Okay, so machine learning is traditionally considered as a subject in computer science, but more and more it is becoming interdisciplinary. So apart from computer science, so apart from computer science, um, there are two subjects of mathematics from which machine learning borrows a lot from. One is what is called as optimization, and the other is what is called as statistics. And machine learning also borrows a lot from the subject of neuroscience, which has again a lot of connections with folks working in biology. Now, coming to applications and complex problems, machine learning has been successfully applied in many application domains, but there are two particular domains which go by the name vision and speech. So, these are basically applications where which are based on visual perception and audio based perception. So it has been established that current machine learning algorithms achieve human level performance or sometimes expert level performance in basic cognitive tasks in these domains. Again, this is very interesting that humans match that machines can match human performance or sometimes surpass them, but I would like to re-emphasize the fact that this is only on basic cognitive tasks. For example, in case of vision domain, basic tasks would be something like recognizing objects in an image, and in speech a basic task would be transcribing what is being spoken, and so on and so forth. So on such basic tasks, yes, the performance surpasses human level, but this is not so machines are far from achieving the kind of performance in case of high level tasks, like perhaps creativity or summarization, or thinking about solving some very interesting or innovative inference tasks. So in such kind of high level cognitive abilities, humans are machines are of course far from reaching human level performance. Nevertheless, even though the success is in case of basic cognitive abilities, mixed with the power and potential of computers, uh, it has far reaching implications in real world applications. So it has seen a lot of success in vision and speech, also moderate success in other applications. And of course, our interest is in biology. So let's give you a glimpse of the success of machine learning in healthcare industry. So most of the success of machine learning algorithms happened in the industry, happened in case of medical imaging and related industries. So here I just give you two examples of these industries. And again, as one can easily understand, the success is basically because the current algorithms, state of the art machine learning algorithms, achieve good performance already on vision domain. So as long as visual perception basic tasks are handled, of course you can expect that the same thing happens in processing medical images, right? So this is why there's been a lot of success in medical imaging related applications. Similarly, the other case where there is a lot of success is that of assisted living, where the idea is to continuously monitor maybe disabled or old age citizens, or to assist them using speech recognition based applications, and so on and so forth. Again, because of the success, this again can be attributed to the success of machine learning in vision and speech related domains. Um, there's another application in which application in which machine learning has shown a lot of promise, and that's the case of computational systems biology, where the idea is to study the take a systems level approach to biology and look at the overall picture rather than the picture in each of the cell, or tissue or something like that. And there are these two companies which heavily use machine learning algorithms to solve problems in system biology. Um, Especially machine learning algorithms have shown a lot of promise in predicting the gene expression levels from high throughput data like microarray data. Not only healthcare industry, machine learning giants like and Google have started to now invest a lot in healthcare, right? So that's another sign which shows basically the amount of potential or the belief people have in the potential of machine learning for solving problems in healthcare. Okay. So now that I have given you enough motivation about why, about the success of machine learning, so let me uh, go ahead and introduce you to machine learning at a slightly more detailed level. And before that, I would like to clarify the difference between many terms you would have heard elsewhere, which are related to machine learning, and some of you might be wondering what is what and what are the differences between them. So it so happens that artificial intelligence, which many of you would have heard, happens to be the biggest subject, the mother subject, of which machine learning is simply a subset, and the popular deep learning happens to be a further subset of machine learning. And data science, which also you would have heard perhaps from other sources, is a subject which has a big overlap with artificial intelligence, but it but it is not a subset, because it also focuses on other aspects like data storage and communication and so on and so forth, right? So this slide is just to give you a clarification of what all these terms mean. So sometimes these terms are used interchangeably, in an informal sense. Okay, so okay, so this is the perhaps the most important slide, the basic slide about machine learning. So in machine learning, as we have said, various cognitive learning tasks have been formally studied, and these formalizations have been categorized into three cases. So there are three standard settings which are very well studied and well understood, and over 2 to 3 decades of research has happened in each of these standard settings. So the settings are called as supervised learning, unsupervised learning, and reinforcement learning. Essentially, supervised learning and unsupervised learning formalize the cognitive learning that happens in human beings, which is based on examples, right? So many times humans learn concepts through examples, right? For instance, consider how a mother tries to teach her child, um, to recognize various fruits, right? So what does the mother do? She basically presents various examples of fruits and actually spells out each of the fruit names, right? So this is a classic example where learning happens through examples, right? So the baby now starts to recognizing various fruits, right? Now entirely um, different kind of learning also happens in human beings, which is called as learning which is based on trial and error, right? For example, consider how a baby learns to roll over or crawl, right? So this is definitely not based on examples, right? It is not that babies see other adult human beings around it crawling or rolling over, right? Most of the time perhaps it sees human beings who sit or stand or walk or run and so on and so forth. So this is an example of a case where learning does not happen through examples, but it merely happens through trial and error. The baby actually tries various things, and some actions succeed and lead it to the success. Like, perhaps the baby wants to reach a particular object, and it tries various th- things, and hence it learns how to roll over or crawl or so on and so forth. And this is what is formally studied in machine learning under the name reinforcement learning. And each of these standard settings have enormous applications in medical field, in healthcare applications, and they also have a lot of potential to be exploited further. So let me give you a closer look at what supervised learning is all about. So in supervised learning, there is some abstract concept that is to be learned. For example, recognizing various fruits, that could be a concept that has to be learned, right? Now the way learning happens is there exists some supervisor, which example is the mother in case of the baby learning, right? What does the mother do? She simply picks various examples from the concept, right? For example, the mother shows an apple, which I call here as O1, and actually labels the apple as L1 apple, right? Similarly, it perhaps picks another fruit O2, which is say an orange, and gives establishes its label as L2, which is perhaps the word apple, right? So on and so forth. So basically what the supervisor does, the supervisor merely gives a collection of examples, which are labeled, and which actually expose the concept in some fashion, right? um, Now this such set of examples is what is called as training data, right? Okay, now this is what the supervisor does. Now in fact, if one observes very carefully, each example itself, I have actually split it into two parts. One is the part which represents the visual perception of the object itself. For example, you just show an apple, right, and then you actually say it's an apple, right. Now, though it looks like it's one example, the example can be split into two parts. One is a part which is based on purely the perception of, which is left to the perception of the learner, which is nothing but the visual appearance of the fruit in this example. And then actually the part where the mother tags or labels the fruit with the name of the fruit, which actually is the information that the supervisor is providing, right. So there's a small you know variant of supervised learning where only such observable part of the examples are only shown, and the actual information that is provided by the supervisor, which is represented via these labels, is completely hidden to the learner. For example, this is what happens in what is called as unsupervised learning, where there is no supervisor. There are just some examples of fruits perhaps shown to the baby, and it is of course believable that at least humans, just presented a large examples of say fruits, they will after some time tend to recognize what fruits are of one kind, what fruits are of another kind, and so on and so forth, right. They may not be able to infer the label of each of the fruit, but definitely they'll be able to categorize the fruits, right. So this is what is formally studied in unsupervised learning. So there is a very small difference which is between supervised learning and unsupervised learning. Both are example based. One has the extra information that comes from a supervisor, whereas in the other, the supervised part of the information in the examples is completely hidden, and hence it's called unsupervised learning, right. So otherwise both these setups model the same kind of learning, which is based on examples. Okay, so now get back to supervised learning. So this is what is called as the training data, and this is the first input which comes to the learner, right? So in machine learning, the placeholder for learner, for example, the baby, in case of the fruit learning example, is called as the model. Model is nothing but some kind of a statistical model most of the times. I'll give you some examples shortly. So this is nothing but the placeholder for the state of a learner before cognitive learning happens. Right now, the learner is presented with the training data, and then what is called as a training algorithm runs. Training algorithm is nothing but the placeholder for the algorithm which mimics or imitates the cognitive learning that happens in human beings. Right. So this is what is the most interesting part, perhaps. Um, of machine learning. And then the learner improves its cognitive abilities, and what is the end product of this training algorithm is what is called the predictive model. Predictive model is nothing but a placeholder, a formal placeholder for representing the state of the learner after learning happens, right. And of course, once a predictive model um, one can simply ask the predictive model what is the label for a new fruit image, and you would perhaps get the right label for the corresponding image, for corresponding fruit, right. Okay, so this is basically the um, typical pipeline of supervised as well as unsupervised learning. Um, and I have also, so let me further explain supervised learning through a example from cardiology itself, because this is the conference. Um, So consider the problem of classifying coronary artery plaques, and this is the work by Zurich and his friends. Uh, Now there are, as we discussed earlier, there are two main ingredients which go into learning. One is the training data, the other is the model. So this slide basically shows how training data is collected to solve this problem. So what Zurich et al. Do is the following. So they took medical CT angiograms of 98 patients, and then they did some basic pre-processing, image-based pre-processing of these angiograms, from which they get a 3D image of the centerline artery. So this is nothing but a representation of the 3D image of the centerline artery. By the way, so this process entirely is image processing. There's no machine learning here. So there are some standard image processing algorithms which take angiograms and then give this as the output. Now each of the observable parts O1 to O98 of these 98 examples are nothing but images of centerline arteries of different patients, right? As simple as that. And then what they have done is they have taken each of these angiograms and showed them to actually some doctor or radiologist, who actually labeled these angiograms as having plaque or not having plaque. And if they have a plaque, they further classified them into whether they have a calcified plaque or a non-calcified plaque, or is it a mixed case, and so on and so forth, right? So these are what constitutes the labels, right? So L1 could be, for example, a calcified plaque, L2 could be a non-calcified plaque, L3 could be a mixed case, L4 could be a case with no plaque, and so on and so forth, right? Okay, so this is what is the training data, which consists of pairs of processed angiograms labeled with whether there is a classification, if so what kind of classification, and so on and so forth. Okay, now the other most important ingredient of learning is actually the model. So here I try to describe informally a popular model which can be used to solve this problem, called as convolutional neural network, CNN in short. Um, so again, this is a very high level informal description, just for the interest of the audience here. So let's see. Suppose a human being who is not an expert in analyzing angiograms is presented with such data, training data. What would then the human do? Perhaps any reasonable human being would do the following. He would first of all categorize these medical images into each of these four classes. What are the four classes here? Perhaps this is calcified plaques, this is non-calcified plaques, and this is a mixed case, and maybe F4 means no plaque at all, right? So he first perhaps classifies all the existing labeled medical images into these categories. Then perhaps he looks at all images that belong to no plaque case, and then see what are the unique signatures that are unique to this class, which are absent in other classes, right? So this is what anybody would do. He would look for some kind of patterns or signatures which exist only in a class but are absent in the other classes, right? So CNN model exactly does the same thing. So the model is nothing but a collection of candidate signatures. So here I show an illustration where this is maybe a 4 by 4 sized candidate signatures, and then many candidate signatures. In fact, a CNN deals with all possible candidate signatures of a particular size, and then it also can handle various sizes. So here I show candidate signatures of a lesser size, 2 by 2 pixels. This is 1 by 1 pixel, so on and so forth, right? So the model is nothing but a set of candidate signatures of various sizes, and the same story repeats for each of these classes. And this is what is the model, and what the training algorithm, very similar to how a naive human being, a normal human being would, non-expert human being would do. He would simply try to see which of these candidate signatures are actually uniquely present in a particular images of a class, right? So perhaps this would be matched to this part of the image, would be matched to the other part of the image, similarly to all images of a class. And finally, what one would be interested after the training algorithm, so the goal of the training algorithm would be to find in each class what are the candidate signatures that have the maximum in class match and minimum out of the class match, right? Basically try to find signatures that are unique to a particular class, right? So happens, and this is what is actually the predictive model in this case. So for each of these classes, actually these are this suppose, so this is just an illustration to show the actual signatures that are inferred to be unique as per the given training data, right? Now given a new image, one would again look for a match for each of these candidate signatures, and whichever signature has the maximum match, in this case F1, would be declared as the label for this patient, right? So this is how perhaps a simple one can implement a simple supervised learning based model for solving the problem of coronary artery, for identifying coronary artery plaques, right? Now in the remaining part of the talk, I would also like to introduce you to the interesting problem of reinforcement learning, which actually also finds natural applications in healthcare. So consider the problem of finding the best drug through clinical trials. Okay, so because now corona is everywhere, let's assume that the problem, that the disease to be solved, handled is coronavirus, and then there are three candidate drugs that have been designed from medical prior knowledge, right? So drug one may be malaria drug, drug two some other drug, drug three some other drug, right? Now based on clinical trials, we want to find out which is the most effective drug for killing the coronavirus, right? Let's assume that the unknown success rate of each of these drugs is 0.8, 0.85, and zero point 0.9, right? Now, of course, the goal of any set of clinical trials would be to find the best drug, that is D3 in this case, right, which has a 0.9 success rate. But of course, this is not known. Um, while the goal is to find D3, the other goal is also to find D3 in the minimum number of trials, right? Or in other words, in minimum, in the trials should the number of trials in which the suboptimal drugs are employed, that is D1 and D2, are minimized, right? So the number of trials in which the suboptimal drug is used is actually defined as what is called as regret. So in simple words, the goal of clinical trials is to actually learn the best drug through trial and error process that minimizes the regret of the clinical trials, right? Regret, we mean the number of trials in which the suboptimal drug is employed. Of course, it's a very challenging problem, right? As you're seeing, if somebody has to guarantee that the number of trials in which the suboptimal drug is employed, the identity of the optimal drug should be known, right? But that's not known, then that's exactly the unknown in the problem, right? So how would one then go about solving this problem, right? um, just to illustrate to you what is the important trade-off that that is hidden in this clinical trials experiment, let's assume that somebody has conducted 10 trials, and the empirical success rate, that means 9 of the 10 cases happen to be 9 of 10 cases in which drug 1 was employed happened to be successful. So this is the empirical success rate of drug 1, similarly drug 2 and drug 3, right? Now so this is just some initial set of trials. Now you want to continue further trials to establish what is the best drug, right? Now the person who conducts the lab, or the researchers who are confronted with this problem are face this important choice, that in the next trial which drug do they have to administer? Is it drug 1, drug 2, or drug 3, right? Note that the true success rates are completely hidden from the researchers, right? Okay, Now there's a important trade-off which happens here, which is called as the explore exploit trade-off. So let me explain that. So one idea could be to employ the drug which has the highest success, highest empirical success rate. Now let's see what happens if we do that. Then we would obviously pick D2, which happens to be suboptimal, by the way. So we would employ D2, and perhaps if you keep employing drug 2 till ultimately we know that this number would converge to 0.85, because if you have the luxury of conducting infinite number of trials, then of course all these numbers, empirical numbers, would be same as the unknown success rates. Right now, as soon as this number goes below 0.9, drug 1 will be selected, right? And sometimes, and then after some time, D1's rate will start converging towards 0.8, so then you'll start picking drug 2, right? So what will happen is you'll keep conducting clinical trials, and then employing drug 1, drug 2 alone, until their rate of the success rates is doesn't move much from 0.8 or 0.85, because you have conducted many trials. So these drug 1 and drug 2 have been tested enough number of times, so perhaps they'll stabilize at 0.8, 0.85. Okay, and then you will start, because 0.85 is a bigger number, you will start administering drug 2 always. And what is the problem with this method? Of course, the problem is that just because D3's empirical success rate, because it was tried very few times, happened to be 0.75, this drug D3, which happens to be the best drug, the optimal drug, is actually never discovered, right? Never explored, right? So this is the problem with what is called as exploitation. Exploitation is nothing but you administering the best drug according to the current knowledge, right? Current empirical results. So one has to explore suboptimal drugs according to the empirical trials, right? That is clear. But what is the problem if you just explore? If you randomly explore drugs, then obviously there is no guarantee that you would you would use the optimal drug, right? So there's clearly a trade-off between exploring and exploiting, and interestingly, a very theoretically sound algorithm which guarantees that the regret of an algorithm called UCB is the least among all possible algorithms in the world, right? That means no other algorithm in the world can achieve, will administer the wrong drug lesser number of times than this algorithm, right? Note that this is a guarantee given by the algorithm even without any knowledge about what is the true success rates of these drugs, right? So this is just to show you a glimpse of it's like a trip of the iceberg. I wanted to show you the kind of potential which the theoretical results in reinforcement learning might have in the healthcare industry, right? So let me summarize my talk by saying that machine learning seems to have immense potential for healthcare applications, and it has been established that in certain medical imaging and assistive care applications, expert level performance is observed by current state of the art machine learning algorithms. And there are many other standard setups like reinforcement learning which have not been yet explored well in healthcare field, but have a lot of potential to be applied in healthcare, right? So once again, I'll thank the organizers for giving me this opportunity. Many thanks.